ABC Newcastle.
Let's blow some bubbles together, although these ones aren't as easy to see as the ones in the bath or when you're doing that bubble art with kids. These are nano-bubbles. And there's something else. They're proving essential in the separation of valuable minerals and all the rocks and earth that they come in. That's where the extent of my knowledge stops. So let's meet someone who knows all about it here in the Hunter. Turns out we have a nanobubble expert in Dr Subhasish Mitra. Good morning.
Good morning, Kaya.
Nanobubbles, what are they?
Nanobubbles, they are gaseous entities, and you'll be surprised to know they are 400 times smaller than a human hair strand. So basically, they're invisible to the bare eyes,
Yep.
but they exist. Research shows they exist. And I'm also trying to figure out how.
Yeah.
And they have great potential.
When something is that small, how did we even learn about them, find them?
That's a great question. Basically, there are different measurement techniques are there that actually separates or excludes them from nanoparticles. It's very common to actually have nanobubbles and nanoparticles mixed together. But there are certain analytical techniques actually available that actually classify nanobubbles as purely different, completely different from nanoparticles.
Yeah, right.
So those kind of techniques have been shown in the research.
When something is that small, how are you observing them?
So basically, they come from the signals. So what we have to do, we have to the technique is called dynamic light scattering. So you have got a laser source, shine on these tiny particles or tiny bubbles, and they basically scatter the lights. And on the other side, you have got a receiver that basically takes these signals and convert this signal into their equivalent size. And I'm talking about a size range of 100 to 200 nanometer.
Wow, that sounds big, but it's actually small.
It's actually quite small.
How did you come to work in this space?
So I'm working in the ARC Center of Excellence for enabling eco-efficient beneficiation of minerals. And what we are looking at actually is to separate the valuable minerals efficiently. And one of the ways that can be done is using these nanobubbles, because what's happening that with time we are actually facing more and more lower grade materials. So these lower grade rocks needs to be ground finer and finer. And the conventional bubbles that are used in the mineral processing industry are found to be a bit inadequate to collect these finer particles. So one of the way is to reduce the size of the bubbles. And now we are talking about reducing the size close to this nano range, which are very efficient to collect these fine particles. So making sure they don't end up in waste.
Yeah.
And we are able to collect them as much as possible.
Yeah, because why is that important? Because we're talking about, a lot of mining minerals, copper, nickel, lithium, cobalt. Why is it important that we don't see a lot of waste of these minerals?
So basically what's happening that if we are working with the good grades of material where you don't have to grind them too much, then these the conventional bubbles are okay. But as we head into a low carbon economy down the track, basically a few years down the line, it is expected that we will be encountering more and more these low grade materials, meaning that concentration of the valuables in the ore rocks are really, really low. So you have to grind them as fine as possible to liberate those valuable minerals, and then you actually need these tiny, tiny bubbles to collect them efficiently, because we don't want these valuable minerals to go into the waste stream, basically.
Yeah, we want all of it, especially when it's finite, right? We want every single bit of it that the earth is making, we would like to keep for ourselves.
We have got a finite reserves of them. We need to care for them.
Yeah. So how could this work in practice using nanobubbles, in this way?
So basically, the technology that would be required to produce this nanobubble is called cavitation. So this cavitation can be produced by several by several techniques. So one of the preferred techniques is called hydrodynamic cavitation. What do you do actually? You create a low pressure region in the aqueous body, and what happens? The dissolved gases in the water, they just come out, they form the nucleate and form these tiny bubbles. Now, there has been a great debate that why do even they survive? And there's still research going on. I'm interested in that. You'd be amazed to know that their internal pressure of these bubbles can go as high as 30 times of the atmospheric pressure.
What?
30 times of the atmospheric pressure, which is basically like, 30
in that
bar.
tiny bubble that you can't see with your eyes.
Theoretically, it can go up to that. But then we are wondering what makes these bubbles survive. And the most accepted theory currently is that they actually have got an electrical layer surviving on their interface that gives them that strength so that can withhold that kind of internal pressure. So that's the current theory at the moment.
Yeah, right.
We need to see how good that theory is.
I feel like the question is, what can't these bubbles do at this point? They just feel like the more we learn about them, the more amazing they've become, right?
They are really mysterious thing. But they can do amazing job. Like some of my work actually shows that when you mix them with the particles, the particles actually form. They act like a glue. So they actually bring all these particles, stick to the particles. They make it a cluster or agglomerates basically, and then you can have a bigger bubble coming and lifting these particle clusters.
Okay, so if we're putting it through, that ground up material, they bring all the precious minerals, the nanobubbles bring all the precious minerals together, and then we can use the system that we use now to separate that from the waste.
That's correct.
Got it. Are we doing this anywhere, or it's still very much in the early stages?
There are some industrial applications have been reported where they see that if you were utilizing these bubbles, obviously they are not characterized that well, but reportedly they actually contribute to higher recovery of the minerals. But the science behind these tiny entities are not clear yet. And in fact, we need to understand how they survive that long, how long they can actually survive, what gives them that extra strength for their sustenance in the aqueous medium, and how efficiently they can be used for future use.
Yeah, I was going to say, it sounds, I don't know, you say the word nano and it sounds expensive. Like, is this an expensive thing to do to try to get it out? Is that an issue for rollout long term later?
Absolutely, it's not expensive. Basically.
Oh, beautiful.
Yeah. All we need to do is just a normal pumps or that actually we use, and we need to just throttle that pump basically and create some low pressure. So we are not really talking about any expensive, equipment or anything in that matter to create these nanobubbles. So the name is definitely a bit extraordinary, but they can be very easily produced.
Yeah, okay, well, that's good to know. What does it mean for, I guess, sustainability in these type of operations as well? Because that's the big question. When we are talking about any sort of mining for ores or minerals, we want to make sure we're doing the least amount of damage. How does this fit into that wider conversation? So
basically what's happening that we are going into a low carbon economy soon. Okay, so we are shifting away. There's a paradigm shift going on. We are shifting away from the fossil fuel to a green economy, where minerals are going to play a great role. Now, wind turbine, electric vehicle, you name it, you'll find copper, nickel, and smartphone, basically. Do you know there are 40 different minerals you use in your smartphone, basically? They all have to come from these mineral resources. And what we have to make sure that we make most of them, making less rejection in the tailings and reducing the impact on the environment. And that's what the ARC Center of Excellence is committed to, finding out the transformational technology that actually reduces the environmental footprint and making efficient usage on extraction or beneficiation of these minerals.
Yeah. The more we learn about nanobubbles, do you see them being used in wider parts of science in our community as well, not just when it comes to, extracting minerals?
They actually have a wider range of usage. They are utilized in the wastewater treatment. They can be easily utilized there because they've got a fantastic oxygen transfer efficiency. So for wastewater treatment, they are a great agent. And you can also utilize them for enhanced growth of seeds, basically, for germination. Yeah, what these nanobubbles have got, they have got this excellent capability of oxygen transfer. And for life to happen, basically, you require that oxygen. So in agriculture, yes, you can use that. In aqua-based farming, yes, you can use that. For fish farming, yes, you can use nanobubbles. All they do, they increase the amount of oxygen that this aquatic animal or any seeds or anything in that matter, basically, whatever, if they require this oxygen, the nanobubble can actually transfer that oxygen very easily. So if there's a growth for life, nanobubbles supplies that oxygen.
So they'll make me a better gardener, or not so much?
I think they might actually, Kaya.
I'll finally be able to grow something if I can make some nanobubbles in my backyard. Is that what you're telling me?
Yep, you can definitely do that. You can have a nanobubble water and just put it into a garden, and we will see whether that plant grows a bit better than your ordinary watering of the system.
I could still be the problem even if there's nanobubbles. So it's amazing work, and I'm really excited to learn more about it as you learn more about it as well. Every time you learn something, you must have some more questions, right?
Definitely. It's the underlying science or physics of how these bubbles actually survive, how they're attaching to the particles. That's what basically I'm looking at. Understanding the physics, developing mathematical models to describe that. Yes, so each day we learn, and we are closer to our final goal.
Yeah, that's why you do the work you do, right?
Yep, absolutely, absolutely.
Really lovely to speak with you today to learn more about the work that you're doing. Thank you for coming in and talking us through it.
Thanks, Kaya, for having me
Anytime.
in your studio this morning.
Thank you. Dr Subhasish Mitra, their chemical engineer at the University of Newcastle, working with those teeny tiny invisible bubbles, the nano-bubbles, to separate, the minerals that get left over in some of those tailings, so that we get every single piece of those precious minerals. This is